Hello everybody, I'm back with another video here. We're moving into the chapter on chemical equilibrium, and so I would argue this might be the most important chapter in Chem 2, in General Chemistry 2. This chapter sets the stage for pretty much the majority of the rest of the course, the ideas here. So even though it starts out pretty simple, I would really pay attention to the videos in this chapter. You should pay attention to all of them, but these are the most important, I would say, of the semester, and one of the most important in general chemistry and chemistry in general. So we're really in the heart of thermodynamics in this chapter. We'll talk about equilibrium, but first let's talk. This video will introduce some ideas and some terminology, some definitions, if you will. So I'm denoting here a reversible reaction. It has a forward direction and a reverse direction, and you can have a rate for those directions. So this reaction is just hydrogen gas, iodine gas forming 2HI. It's balanced stoichiometrically, so we can have something we'll call the rate forward. I don't want to write it all the way out. I'll just write RF, meaning rate forward in that direction, and rate in the reverse direction. I'll just call it R sub R for rate. That's kind of weird looking. I'll call it R rev, reversible, the reverse direction. So that's the direction going this way. I use any kind of arrow I feel like. There's no meaning if I draw an arrow like this or like this. Some books have specific meanings for it. In my notes and in my writing, I have no meaning other than it's going in a direction. Sometimes I'm too lazy to draw a double arrow. So it's an arrow that's looking like a double arrow in one direction and the other. It means it's a reversible reaction. So we can write a general form of this just for an arbitrary reaction. I like to do that to set things up. Where the lowercase letters denote the stoichiometric coefficients of a balanced equation, and the capital letters will denote the chemical identities, the chemical species, molecules, atoms, ions, etc. And typically when we get going, we can take note of phase as well. Sometimes it's all one phase. We might just say the size all gas phase, but oftentimes we'll often denote it with the parentheses with G for gas and so forth by it. I don't have this in the original form. So in general, let's start out with a gas phase reaction. And I'm going to stick with homogeneous reactions just to keep things simple, at least at first. So let's say everything is in a gas phase. One of the ways that we can characterize this is what's called a reaction quotient. It's typically denoted with a Q. I will use a convention just for my notes and self-consistency when I'm talking about it in terms of pressures. I'm going to, because gases can be well modeled with partial pressures, I'm going to put a subscript P there. You do not need that. I'm just putting that symbol to delineate things. You might find certain books and online sources just call it Q or something else. The way we think about this is that you could take this as a definition. It's a way of characterizing the system. This is just for describing a reversible gas phase reaction will be the partial pressure of species C, I'll put like a capital C here, raised to the power C, and these will be partial pressures, and I'll talk about the units in a second. The partial pressure of species D raised to the lowercase d, so if this was, for example, 2 here, this would be squared. Then you do the same thing with species A. The subscript is just denoting what species. The superscript is a power. And so we have then B raised to the lowercase b. Sometimes it's just 1. In that case, it would be 1. It could be a 2. That would be a 2, and so forth. The input pressures, partial pressures, these are partial pressures, and I'm going to use the convention that these gases will be in atmospheres. You will see some sources that use bar, particularly in physical chemistry books. A bar in an atmosphere about 0.9. They're 99% the same. There's like a less than a 1% difference. So it's for the calculations you'll do, it's negligible. If you are doing research and you come across a table and bar, you can make a minor adjustment for it. I'm going to use what's typically encountered in most Gen Chem books at this point in time as atmospheres. Now here is clearly, let's say these were all to the first power. The units would physically cancel, but there's a convention, and I can explain a little bit of where this comes from in a moment. But let's say it wasn't. Let's say these were all to the first power and this one was squared. That would physically retain units in it. They would have units of one. It would have atmospheres to the first power as units in that particular case, right? And so on the other hand, well, let's see here. If you had atmosphere cubed, yeah, that would be atmospheres raised to the first power. By convention, we report these with no units. No units. Dimensionless. The reason why, this is an FYI, that they have no units is because really fundamentally in physical chemistry or chemical physics, we formally derive these type of expressions using what are called activities, and particularly in solution, we talk about that a lot, not in this course, but in the future. And that's a theoretical measure, if you will, that relates to concentration that's inherently dimensionless. And then we work in the limit of reasonable pressures and molarities, which we'll talk about in a second, where the molarity has roughly the same value as the activity, but it carries units. But we retain the fact that it's reported with no units. So the big thing is that this reaction quotient is reported with no units. Now, that's a generic representation of a reversible system. When it's in the case of equilibrium, so now let's switch the topic, but it's related when you're in dynamic equilibrium. Dynamic equilibrium. Something particular happens. Let's take the reaction over here. When that occurs, when you're in equilibrium, the rate forward equals the rate reverse. That's not true in general. In a reactions proceeding, in general, one of the rates can exceed the other. That's in general. Equilibrium is a particular condition that systems tend to go to. It's the low spot on the couch. It's where you kind of want to head, and we'll put energy to this later. We'll talk about it in terms of the Gibbs free energy, but it's the position in the reaction coordinate where systems tend to as a function of temperature. And when you get there, to maintain yourself, the system it's still dynamic, it still has motion, but the amount of material, the rate of the material moving forward is the same as the rate going backwards. It is not the same. Let's just take a system that's A and B going reversibly, just to keep it simple. It could be equal amounts of stuff going back and forth. Those boxes are supposed to be relative amounts of stuff. I'm supposing they're the same. It does not have to be. You could have a teeny amount of A and a big amount of B with the rate going forward and backwards, or vice versa. It could be the case of them being equal is a special case. You could have a teeny amount of A, you could have a giant amount of A and a little bit of B. It just means that the amount on each side relative to itself is constant. And there is motion back and forth. This has been verified through isotopic studies and so forth. There is motion back and forth. The equilibrium is dynamic, but it just means if, like, I have a big stack of paper and you have two sheets of paper, I have 10 sheets of paper, we exchange one back and forth at the same rate, I still have 10, you still have 2, even though we keep in that exchange going, giving pieces of paper. But in getting there, maybe we started out with equal stacks, and you handed me 2 for every one I gave you, and we kind of flipped around like that until we got to a certain point where we had a ratio that for some reason worked for us. I like a lot of paper, you don't. Maybe that's the situation that occurred. And then we exchange at equal rates back and forth. I've actually heard people who had candidacy for jobs here, one person at least, who was allegedly a physical chemist, say that that means you have equal amounts on both sides. Like drew a picture with equal amounts. That's a special case that can occur, but that's no different than saying there's a big huge amount on one side and a little teeny amount on the other. It's no different, no more probable than that. So what we can do here on the equilibrium condition, let's focus right now on the gas phase, is write not a reaction quotient Q, but we write what's called the equilibrium constant. So in this particular case, we write what's called an equilibrium, I can't spell, constant, and we denote it with K. Everything else is the same. It's got partial pressures written for the particular species raised to the power. We'll just do the example of the iodine above reaction, raised to the power of the stoichiometric coefficients. Its input is atmospheres, but regardless of if units are left over rigorously, we report it by convention in tables and so forth with no units. So that is for the gas phase. We input the partial pressure. And so for this system, I don't know what the numbers are, but at equilibrium, it would follow the math like this. It would be the partial pressure of HI squared. It would be, input would be atmospheres. And then we would have the partial pressure of H2 and the partial pressure of I2, both in atmospheres. And we don't write the 1, but there you can think of it as raised to the 1 power. So that's the way we express this. And so we could, we will be solving problems for this. There'll be a number associated with this at a certain temperature. K, this is a capital K, not to be confused with a rate constant. We have rate constants in this discussion because we have rates forward and rate reverse. I will typically draw it as a capital K, and I'll make it kind of bold to make it stand out from an equilibrium constant. This will be a number, and all the K's are a function of temperature. They're a function of temperature. So that's a big point. Now let's take it and go to solution. We've got the same kind of process. AA plus BB going to CC plus DD, capital D. And then for the reaction quotient, meaning the forward rate, the reverse rate and the forward rate do not have to be the same. The Q's are generic. When the rates do equal, Q is equal to K. So K is like the special case, if you will, of reaction quotient. So Q would look like, I'll put, we usually use a C here, and you'll see very commonly in books, a lot of times they call all these K's and Q's, they call the K's at least KEQ, meaning equilibrium constant. I'm going to use capital K with a subscript C, and I'll use Q's with subscript. Sometimes I forget the subscripts on the Q's, but I'll be comparing it to a K, so you can just put a subscript on. Now we use molarity. We're going to focus on aqueous. This is applicable to all solution types. It's the species C raised to the C power. It's the species D, molarity, raised to the D. It's the species A raised to the lowercase a, stoichiometric coefficient, and B raised to the lowercase b. So that would be an example. The input is molarity. So you have to know how to calculate molarities. The output by convention, no units. Same argument, and the argument about the activities really explicitly clear here, because that's usually where we talk about activity more so than in gas phase, is in solution. Also note, here's a big also. We've got ideal gas law, PV equals nRT, right? Well, we can take, there's a relationship, we have volume and N, right? You could take V and N, right? And that's equal to RT over P. When you got pressures, you can relate it to concentrations. This is, well, we can, well, actually, let me flip this around. I can write that, that's V over N. I can write N over V is equal to P over RT. That's another way of writing that, P over RT. We can relate, and I'll make a link between these later on in another lecture. This has units of molarity, moles per volume. We could make this moles, and we could make volume, instead of meters cubed, we could make that liters, right? Meaning, another convention here in the aqueous phase is, well, let me say this. In the aqueous phase, we're only going to report this in terms of molarity. In the gas phase, we can also report, instead of having it in terms of QP and KP and QP, we can also report the Q in terms of have it in this form with the molar concentrations. We can do that as well. So for gases, we can do it with the KP QP set, but we can also do it with QC and KC. KC looks the same as this, except it's at equilibrium. So when the forward and reverse reaction are the same in solution, you can write it in the same form. It just means the reverse and the forward rates are equal. You can apply this form with molarities to both solution and the gas phase. But if you're in solution, you only will use the molarity form. And so that's the big thing to know. It's products over reactants. It has the exponents are related to the stoichiometric coefficients. You can use the form with the partial pressures for the gas phase. You can use the form with the concentrations for solution or the gas phases. The K's denote equilibrium condition. The Q's are reaction quotients for any old time. They give you concentration ratios for any position along the reaction coordinate. So this is all covered on pages 1 and 2 of the note sets written out. So if we want to take the above reaction, which is in gas phase, the one with the hydrogen, the iodine, and treat it in terms of molarity instead of partial pressure in atmospheres, we could write Kc is equal to Hi squared molarity, and we have H2 and I2. And I will say now, Kc in this particular case will equal to K sub P. It's not always the case. We'll get to Y in a little bit. So on page 2, there's a nice summary. It says the input, so we have here with QC, Kc, and then we have, let's put QP, Kp, input. Here, molarity. Here, pressure, and we want to put that in terms of partial pressure. In atmospheres, again, you will occasionally see it in bars. The output, no units. No units. The what's not allowed, this applies for both solids and pure liquids. Liquids do not go in there in either case. Solids and liquids do not go into these expressions. The term for these expressions is the law of mass action. That's what it's actually called, the law of mass action, although I'll just typically say an equilibrium expression or a reaction quotient. That's what it's formally called. So those are some of the big ideas. Solids do not go in. Let's give an example where you can see that real clearly, because that's solids and liquids not going in. It always seems to get people. So let's take a reaction. This one, I've put this on test before and people get it right. Let's take calcium. I'm going to, board's giving me a little problem here. Calcium carbonate, solid, reversible equilibrium with calcium oxide, solid, and carbon dioxide gas. CO2 gas. So in that case, let's say we wanted to do it in terms of, let's focus on equilibrium constant. The reaction quotients follow the same rule set in terms of what we can write. So if we wanted to write Kp, it would be, we ignore this is a solid, it'd just be the partial pressure of CO2 is in atmospheres, whatever it is. And we would write Qp similarly. Qp would be partial pressure of CO2. If we wanted to do it, this says the species is in the gas phase, so we could do it in terms of a Kc. Kc would be the molarity of CO2. And Qc would be equal to the molarity of CO2. On that note, I'm about out of time on my phone. I do this all on my phone. Hopefully the lighting here is good. I blow these up and ensure that I can see them. With my eyesight, I can. If you're having a hard time seeing it, I suggest blow it up a little bit. I'm doing this at home before the semester starts to give us a good head start. So on that note, I'll make another video on this. This is note set on chemical equilibrium, which is online. You can look at that. So you can start reading that really important set of notes. On that note, have a good night or a good day.